So this is lesson 8, and what we're going to talk about here are vectors. So I have a little clip for you guys just to get us in the mood for vectors, and I'm not going to lie, I've been waiting to show this to y'all all semester.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
So some quantities are determined completely by their magnitude, and some examples of this are length, mass, area, temperature, energy. So these are those quantities that don't have a direction, they just have a length or a magnitude. And we call such a quantity a scalar. So these are just your run-of-the-mill numbers like 1, 2, 3, 4, 5, 1/2, pi, those kinds of things. But if you think about something like displacement, it involves both a magnitude and a direction. So if you think about velocity, you could go either forwards or backwards. So you might have something positive or negative. Acceleration's kind of the same way as is force. So these quantities have both a magnitude and a direction, and so we call these directed quantities, and mathematically we can represent these with vectors. So all a vector is a directed line segment. And vectors are kind of cool because you can look at them in a few different ways. So first we're going to look at it geometrically just so you can get some of an idea of what we're doing, and then we're going to move on to some actual like algebraic computations. So a geometric vector, we have an initial point. So let's say this is our vector to the right. Let's call this point P and that point Q. So the initial point will be point P, and that's where the vector starts. The terminal point will be Q, and that's where the vector ends. So vector starts, vector ends, and every vector is also going to have a length or a magnitude, and this would just be the length of the line segment P to Q. Okay, so we call two vectors equal if they have the same magnitude and the same direction. So when you're determining if two vectors are equal, you have to check both of those things. So for example, let's say that this vector here was our vector. This would be equal to a vector that is the same length and in the same direction. So a vector that looks kind of like that. So those two would be equal. However, let's say that we had a vector that was in the same direction, but maybe it was half as long. So like, let's say it looked like that. So that vector all the way to the right would not be equal to the other two because the length is not the same. Another thing you could do is you could have the same length, but let's say the direction gets changed. So let's say we're going up instead of down. So this would also not be equal to the other three vectors. Okay? A vector v written in the plane PQ is the set of all directed line segments that are equivalent to a given vector PQ. So vectors can be in any position on a coordinate grid, and we tell if they're equivalent if they have the same magnitude and the same direction. And so a vector in the plane can be represented with many different line segments, true or false, and that would be true. So it really just depends on the direction and the magnitude, but it can be in any position on the coordinate grid. Okay, so we're going to talk now about some vector operations. So of course, those were just some definitions. Now we're going to get into actually doing math with vectors, because vectors are really important in your applied maths. You might see it later if you take Calculus 3 and linear algebra as well. So with vectors, we have two basic operations. We have addition and we have scalar multiplication. So with vector addition, if the initial and terminal points are the same, the vector is the zero vector. And we denote this as a 0 with a little arrow over it. So if you think about the initial and terminal points being the same, so let's say we have a point somewhere in space, and let's say that that's your initial point. If your terminal point was in the same exact space as that, obviously you're not going to have really a vector, you're just going to have a point. And so it's kind of like adding 0 to a vector that you already have. And so that's why we call it the 0 vector. Now the sum of non-zero vectors, we can do this geometrically by placing the initial point of one vector at the terminal point of the other vector. And the resultant vector from this is the sum. So let's say that this vector across the bottom is vector u. And let's say that this vector on the side is vector v. Then the way we would add vector u to vector v is we would kind of complete this triangle here. So we have the starting point, or the initial point, and we have our terminal point of our entire path. So this would be the sum vector u plus vector v. And I should probably mention that almost any time we write vectors, we usually specify that they're a vector by drawing that little half arrow above whatever letter you're using to name it. Now, if u and v start at the same point, then u plus v is just the diagonal of the parallelogram formed by u and v. So let's say that your vectors are set up this way instead of as they were in the last example. So again, vector u will be this vector along the bottom, and vector v will be that vector on the side. Now you can kind of turn this into the previous example if you were to rewrite vector v over here, right? So we could rewrite vector v over here, and again, you could find the resultant vector simply by completing that triangle. So that would be u plus v, okay? Now if you notice, this kind of forms a parallelogram. And if you're not familiar with what a parallelogram is, it just means that the opposite sides of that kind of slanted rectangle are parallel to each other. So if you look at that diagonal of the parallelogram, that's going to be the sum of your two vectors. Okay? The next thing we want to talk about is scalar multiplication, and this is just a really fancy term for we want to multiply your vector by a number. So if we have a real number and a vector, then the product a times a vector v has magnitude, we want a times the magnitude of v. So the magnitude of a times the magnitude of v, and it has the same direction as v if a is positive, and it has the opposite direction of v if a is negative. So a is that number that we're multiplying by v. So let's look at a few geometric examples here. So if we start with our vector v as this vector right here, let's say that we want to multiply v by 1/2. So this would give us a vector in the same direction, but it would be half as long. So our vector 1/2 v might look like this. Okay? Now let's say we wanted to multiply v by 2 instead of 1/2. So it would be very similar, except now your vector would be twice as long instead of half as long. So it would be 4 lines long instead of 2, and it might look something like this. Okay. Now next we have negative v. So what that negative tells us is that the direction is going to flip, but will have the same magnitude as our original vector. So it will still be 2 lines long, but instead of pointing up, we're going to make it point down. So it might look like that. Okay, and finally we have negative 1/2 v. So this means that we're going to flip the direction as well as multiply by 1/2. So we'll have a vector pointing down that's half the length of v. And so that would look like that. Okay, so that's just a little geometric way of how scalar multiplication works. All right, so you might be wondering at this point, well, if we added two vectors u and v, can we also subtract two vectors u and v? And the answer is yes. So the difference of two vectors, u and v, looks like the following. So we can think about this as adding a negative. So whenever you first learned about negative numbers, your teacher might have told you that there's really no such thing as subtraction because you're really just adding a negative number. And that's kind of that's really how you want to think of subtracting vectors. So we could look at the same setup that we had before. So let's this time call this vector u and this vector v. Okay, now to find the difference, what we need to do is think about the opposite vector to v and then add it to u. So if we think about the opposite vector of v, it would be a vector with the same magnitude as v, but going in the opposite direction. And we would write this, if we were going to use this geometric tip to tail method, we would put our initial point at the terminal point of u, and this would be negative v. Now if we want to add u to negative v, remember all we need is the diagonal of that parallelogram. So if this is the initial point of our path and this is the terminal point of our path, then this vector here is going to be u minus v. Okay, so hopefully that makes a little sense. So now that we've kind of looked at vectors in a geometric sense, we're going to translate this to an analytic or a numerical representation. So if we place a vector v on a coordinate plane and go from the initial point to the terminal point by moving a units to the right and b units up, we can represent vector v as an ordered pair of real numbers. So we want to stay away from complex numbers, even though I know that we just talked about that a lot in the previous lesson. So we're going back to just the regular xy plane. So as you can see here, a vector you write as an ordered pair, except instead of parentheses, you use these little diagonal or triangular brackets there. Okay, so for example, let's just say that we had the vector I don't know, 2, 3. So let's say we go over 2 and up 3. So that would be the terminal point of your vector, and we're just going to assume that we started at 0, 0 here. So this would be the vector 2, 3. Okay, so again, just like an ordered pair, but by using those triangular brackets, we're saying that this is actually a directed line segment. Okay, so we call A the horizontal component, and that should make sense because it's also that x coordinate, and b is the vertical component of the vector v. So we're just dealing with x and y coordinates, it's just we're calling them horizontal and vertical components now instead of x and y coordinates. Okay, now that vector a comma b has many geometric representations. So imagine taking that vector 2, 3 and moving it anywhere on the plane. Okay, those would all be equivalent representations of that vector, they're just in different positions. Okay, so that's what I mean by this statement here. All right, the component form of a vector is when the initial point is the origin. So an example of this would be the one that we talked about where we went 2 units to the right and 3 units up, but we started at the origin. And I think your book calls this a position vector, so that's just another name for component form. So if a vector v is represented in the plane with initial point P and terminal point Q, then we can get the component form by subtracting the x's and subtracting the y's and writing that as a vector. So our vector v is equal to x sub 2 minus x sub 1, comma, y sub 2 minus y sub 1. Okay, and you can kind of think about this as you're almost finding a slope because we are talking about a line here. So if you're wondering why this looks a little similar to the slope formula, it basically is the slope formula. Just instead of writing it as a fraction, We're just specifying how many units you go over and how many units you go up. Okay, so that is the component form of a vector. Now we're going back and talking about equal vectors, and so just this time, instead of geometrically, we're going to define it algebraically. So if we have a vector u and a vector v, we know that they're equal if and only if a1 is equal to a2 and b1 is equal to b2. So all this means is that the numbers inside of u and inside of v must be exactly the same and in the same order. And then we know that u and v are equal. The magnitude, or the length of a vector, is given by, and we usually write this in like a double absolute value. So the length of a vector v is the square root of a squared plus b squared. And yes, this should look a little familiar. It is very similar to the magnitude of a complex number because we're still talking about that distance from 0. So if you wanted that geometric explanation again, you could think about a random vector, AB, okay? And you know that it's B units from the x-axis and A units along the x-axis. So what you're looking for is that diagonal distance from 0 to that point AB, okay? And of course, using the Pythagorean theorem, you would get the square root of a squared plus b squared. Okay, so hopefully that should look a little familiar. So now that we've gone through a lot of definitions, let's practice some actual problems, because I think that will help you understand it better. So our first example is find the component form and the length of vector v having initial point 4, -7 and terminal point -1, 5. So the first thing we want to find is the component form. So component form, we have vector v is equal to a2 we'll go with x just so you're not confused. x2 minus x1 comma y2 minus y1. The final point, or the terminal point, you always want to use as point 2. And the initial point you always want to use as point 1. And this is important because if you don't, you'll get something in the wrong direction. So you always do terminal minus initial when you're plugging into these formulas that have those sub 2's and those sub 1's. Okay, so we'll make -1, 5 our point 2 and 4, -7, point 1. And so we want to plug this in accordingly. So the x-coordinate of our terminal point is -1, and the x-coordinate of our initial point is 4. So for the x-coordinate of our vector, we have -1 minus 4. For the y-coordinate, we have 5 as the y-coordinate of our terminal point, and we have -7 as the y-coordinate of our initial point. So we end up with 5 minus -7. And so all we need to do to get our component form is just simplify this. So -1 minus 4 is -5, and 5 minus a -7 is 5 plus 7, which is 12. So our vector in component form is -5, 12 in the triangular brackets. All right. Next, we're going to find the length of that vector. So now that we have our vector in component form, it's not too bad to find the length. Okay, so remember the length is that double absolute value sign around v, and this is just simply the square root of x squared plus y squared. So the horizontal component of our vector is -5, so we have -5 squared. And the vertical component of our vector is 12, so what we get is -5 squared plus 12 squared. And simplifying this, we get the square root of 25 plus 144. And again, simplifying, we get the square root of 169, which is 13. So just like when we did complex numbers, you want to go with the positive version of the square root because we are talking about a distance. And distances will always, always, always be positive. Okay. So let's see what we need to do next. So now we want to actually sketch vector v and its component form. So vector v, to do this, we're going to actually graph the point for -7 and -1, 5. So let's put some notches on our axes here. Alright, so that's, I think, 12 notches on each axis. So now we want to actually graph the point for -7 and -1, 5. So -1, 5, we go back 1 and up 5, so that point would be there. And we also have 4, -7, so we go to the right 4 and down 7. So that point would be right there. So our original vector v looked like this. And make sure that you put the arrow facing the terminal point. So that would be vector v. Okay? Now what we want to do is graph the component form of vector v. So we know that the initial point has to be at 0, 0, and the terminal point will be the point listed in the triangular brackets. So we get -5, 12. So we go to the left 5 and we go up 12. And what you notice is that we get a vector that looks exactly the same as vector v. It's just instead of being at some arbitrary point in the plane, it starts at the origin and it goes off somewhere. Okay? So that is the difference between a vector and the component form of a vector. So now again that we did the geometric operations on vectors, we're going to look at these from an algebraic standpoint. So if we're given two vectors, u and v, then to add them, all we have to do is add the x coordinates and add the y coordinates. So we get a1 plus a2, comma b1 plus b2. All right. To subtract them, really similar. You just subtract the x and y components. So we have a1 minus a2 and b1 minus b2. And finally, to multiply by a scalar, we just multiply each component by that scalar. So the vector u multiplied by a scalar c is just c times a1, comma c times a2. All right. So now let's apply this to some examples. So if we're given the vectors u equal to -2, 5 and v equal to 3, 4, we want to find first 2 times v. So this just tells us 2 times the vector 3, 4. And to multiply a scalar by a vector, we just multiply each component by that scalar. So we end up with the vector 6, 8. All right. Our next one is v minus u. So let's go ahead and write the vector v. That's 3, 4 minus the vector u. So -2, 5. So what we get is the vector 3 plus 2, comma 4 plus 5. So notice we have that double negative here. So that's actually going to be adding a 2 instead of subtracting. So what we get is the vector 5, 9. All right. And finally, we're kind of combining the two operations in this last example. We have v plus 2 times u. So again, I would sub in your vectors. So v is 3, 4. And then we have 2 times u. So 2 times -2, 5. So the order of operations here is the same as if you were dealing with polynomials or just any numerical expression. So you always want to do that multiplication first, and then you want to add your two resulting vectors. So we have 3, 4 plus -4, 10, and we want to add these two together. So we get 3 minus 4 is -1, and 4 plus 10 is 14. So your resulting vector is -1, 14. Okay, so if the geometric operations were a little bit confusing, hopefully these algebraic operations seemed a little bit easier. Okay, so now that we've seen how to do this, we need to talk about all of the properties that you can do with these operations. So let's say you have 3 vectors, u, v, and w, and you have scalars c and d. Okay, so if we add 2 vectors together, it doesn't matter what order you add them in. That's the gist of this first one. So that is your commutative property of addition, just like you have with numbers. Okay? Now, let's say you were adding 3 vectors and you wanted to group together v and w first. Well, this is the same thing as if instead you had grouped u and v first and then added w. So that is your associative property of addition. So again, just like numbers. If we add 0 to a vector, we just get the vector back. And so that is your identity property of addition. All right. Also, if you add the negative of a vector to a vector, that will give you the 0 vector. So that is the inverse property of addition. All right. Now let's say you have a scalar times a sum of vectors. Well, this would be c times u plus c times v. So this is just your distributive property written in terms of vectors. Okay. Now let's say you have the sum of 2 scalars multiplied by a vector. Well, this would be the same thing. You just have c times u plus d times u, and again, that's your distributive. That should be a d. Distributive property. Okay. Now finally, let's say that you have 2 scalars multiplied together in a vector. You could group the scalars as is shown here, or you could group d and the vector u, or you could group c and the vector u and multiply it by d. So this is your associative property of multiplication. There we go. All right. And then if you have 1 times u, you just get the vector back, which is your identity property of multiplication. And if you multiply 0 times u, you would just get back the 0 vector, which is just your 0 property of multiplication. And if you do a scalar times 0, you also get back the 0 vectors. So this is the same property as the previous. Okay, so that was a lot of information, but the gist of the matter is basically with vectors and scalars, we have all of the same rules that we have with regular numbers. Okay, they commute, we can associate them, we have something to add and multiply that won't change the vector, and we can still multiply by 0 and use the distributive property. Okay, so one last little property we have, if we have a vector, which is a scalar times a vector u, then we can get the length of that product vector by splitting it up into the product of the length of the scalar and the length of the vector. And we know that the length of u is going to be the square root of a squared plus b squared. Okay? So anytime you have a product of things like that, you can just break it up into their separate parts. Okay, so the next thing we want to talk about is what's called a unit vector. So any vector of length 1 is called a unit vector. Okay, and two really popular ones that we use are called I and j. And we give them these special names because they really define our xy coordinate system. So I is the vector 1, 0, and j is the vector 0, 1. So think about what these look like on a coordinate grid. So I would start at the origin and go to the right 1 unit. So that is the vector I. And the vector j would be similar, except it would go up 1 unit. Okay, so you can kind of see how this defines our coordinate system, because let's say we multiplied I by any given number. Well, you could move along this x-axis any number you want. Also with j, you could multiply that by any number, and you could move anywhere you want along the y-axis. So this gives us a way to represent vectors in terms of these unit vectors. So we can take any vector and express it in terms of these unit vectors I and j by simply multiplying them by any number and taking the sum. So any vector AB we can rewrite as AI plus BJ. And this is known as the linear combination form of a vector. So same idea we just talked about, it's just a different way of writing it. But we're going to practice using it. So let's find u plus v, and 2u minus v in terms of I and j. And then we want to find their lengths. So first of all, we're given the vector u is -12, 5, and the vector v is 4, 3. So let's go ahead and rewrite these in linear combination form. So vector u will be -12i plus 5j. That's all there is to it. Slap an I on that x component and a j on that y component. Vector v will be 4i plus 3j. Okay, and so now that they're in this form, you can almost think about them like polynomials, because whenever you add the vectors, you're just going to add all the i's together and add all the j's together. And when you multiply, it's also going to look like polynomials as well. So some people like this form better. I don't really mind what form you use, but if the directions specify, make sure to use that particular form. So the first thing we want to find is u, which we already found. So now let's find u plus v. So this is u. Go ahead and box that. Now let's find vector u plus vector v. So we have -12i plus 5j plus 4i plus 3j. And so all we need to do is add the like terms. So -12 plus 4 will give us -8i, and 5j plus 3j will give us 8j. So we have -8i plus 8j for u plus v. Alright, and the last one we want to find is 2u minus v. So we have 2u minus v. So let's go ahead and sub in our vectors. So we have 2 times -12i plus 5j minus 4i, 4i plus 3j. Okay, and now all we have to do is simplify this using the algebra you know and love. So if we multiply by 2, we get -24i plus 10j. And if we multiply the second vector by the -1, we get -4i minus 3j. And finally, we just need to add the like terms. So -24i minus 4i is -28i. And 10j minus 3j is a positive 7j. Okay, so those are our 3 vectors. Now the next thing we want to do is find each of these vectors' lengths. Okay, so the length of u is going to be the square root of -12 squared plus 5 squared. So if we simplify this, we get the square root of 144 plus 25 and this is the square root of 169, and this is just 13. So just as before, your lengths will always be positive. So the length of vector u is 13. All right. Now let's find the length of u plus v. So the length of u plus v is going to be the square root of negative 8 squared plus 8 squared. So we have the square root of 64 plus 64, and this is the square root of 128, which is just 8 times the square root of 2. So you can think about the square root of 128 as 64 times 2, and so we can square root the 64 into an 8, but the 2 we can't square root that. So we just end up with 8 times the square root of 2. All right. Now for our final vector, 2u minus v, we have the square root of negative 28 squared plus 7 squared. So plugging that sum into a calculator, we get that this is the square root of 833, and if you were to simplify that square root, you should get 7 square roots of 17. All right, so hopefully that makes a little more sense as to how we find the lengths of vectors and how we do vector addition and scalar multiplication using our algebraic forms. Okay. Now what we want to look at is, well, we know that we have I and j are unit vectors, but how do we find any unit vector? So how do we take some direction defined by a vector v and find a unit vector that agrees with that direction? Okay, so the way we do this is we usually denote unit vectors by u, and I know that we've been using a lot of u's and v's, but we're just going to go with this for now. So a unit vector u, all we have to do is take that defining vector v and divide it by the magnitude of v. Okay, so we're going to practice with an example. So let's find a unit vector in the direction of the vector v, negative 2, 5, and we want to verify that the result indeed has a length of 1. Okay, so a unit vector from our formula is going to be the vector v divided by the magnitude of v. Okay, so our vector v is negative 2, 5, and the magnitude of v is, let's figure out what that is. So the magnitude of v, we have the square root of negative 2 squared plus 5 squared. So we have the square root of 4 plus 25, which is the square root of 29. Okay, so that is our magnitude of v. So we're going to divide this vector by the square root of 29. Okay, so all we have to do, all we're doing here is dividing by a scalar, so we just have to divide each component by that scalar. So our unit vector is negative 2 over the square root of 29, comma 5 over the square root of 29. Okay, and so let's actually verify that this is a unit vector. So let's find the length or the magnitude of u. So we have the square root of negative 2 over the square root of 29 squared plus 5 over the square root of 29 squared. And this is going to be 4 over 29 plus 25 over 29. And this is just the square root of 29 over 29, which is the square root of 1, which is 1. So from this little algebraic exercise, we see that the unit vector we found has a length of 1, and that's what we wanted. So all this is showing us is that the formula actually works. Okay? Now the direction of v, and you could kind of think about this as a slope, but we usually like to define it in terms of an angle. So rather than just saying we're going you know, up 2 over 1. We want to say that we rotate some angle in the plane. So theta is the smallest positive angle formed by the positive x-axis in V. So it goes back to that polar idea of going over some radius and around some theta. So let's work with an example. Let's find the magnitude and the direction of the vector negative 2i plus 2 square roots of 3j. So here, first thing I would do is again identify your coordinate. So this would be really similar to finding the argument of a complex number. And you can kind of see how it's similar because we've got, you know, that I term added to some j term. It looks really similar. And in fact, we're going to use the same exact formulas. So first of all, because we're going a negative x direction and a positive y direction, we know that this vector is going to end up in quadrant 2. Okay? And that's going to be important when we get to our inverse tangent a little bit later. So first, let's find the magnitude of vector v. So that will be the square root of negative 2 squared plus 2 square roots of 3 squared. Okay, if we go ahead and simplify this, we get the square root of 4 plus 12, and this is the square root of 16, which is 4. So our magnitude is 4. Now for theta, we're going to use that same tangent inverse formula that we used back with complex numbers. So what we get is the tangent inverse of y over x, which is 2 square roots of 3 over negative 2. So if we actually go and simplify this, we get that theta is the tangent inverse of the negative square root of 3. So what we want to think about is what angle in quadrant 2 has a tangent of negative square root of 3. And the angle that might come to mind is 2 pi over 3. So our theta is 2 pi over 3. So what this vector looks like now is, instead of just thinking about it as negative 2 to the left and 2 square roots of 3 up, we can think about it as going out a radius of 4 and going around to the angle 2 pi over 3. So we get that vector looking like this. Okay, so it's kind of like a polar way of looking at vectors, I guess, is a good way to think about it. So the last thing I want to talk about is just how to find horizontal and vertical components using this kind of polar idea. So we'll let v be a vector with magnitude, absolute value of v, and direction theta. Then vector v can be defined by a equal to the magnitude of v times the cosine of theta, and b can be defined as the magnitude of v times the sine of theta. So if you think back to the complex numbers, when we wanted to find that polar form, or we started in that polar form and we wanted to go back to rectangular, remember we did x is equal to r cosine theta and y is equal to r sine of theta. So this is the same idea. It's the same formula. We're just rewriting r in terms of a vector, and of course your radius of a vector is going to be its magnitude. Okay? So let's do one last example. So we know that vector v has length 6 square roots of 3 and direction 7 pi over 6. So we want to find the horizontal and vertical components of v and then write the vector v in terms of I and j. So first of all, the horizontal component we know is the magnitude of v times the cosine of theta, which is 6 square roots of 3 times the cosine of 7 pi over 6, which is 6 square roots of 3 times negative square root of 3 over 2, which gives us, let's see, 6 and 2 cancel. So we have 3 times negative 3, which is negative 9. So our horizontal component of this vector is negative 9, and now we just need to find our vertical component. So we have b is equal to magnitude of v times the sine of theta, which is 6 square root of 3 times the cosine of 7 pi over 6, which we get is 6 square roots of 3 times negative 1/2, which again the 6 and the 2 cancel, so we get negative 3 root 3. Okay, so your horizontal component is negative 9, vertical component is negative 3 square roots of 3, and finally we just want to write vector v in component form, or in linear combination form. So vector v, I'll just go ahead and do both. So component form would be negative 9, comma negative 3 root 3, and linear combination form would be negative 9i minus 3 root 3j. Okay, so that's a basic introduction to vectors. So make sure you're working on all of this homework. It looks like a lot, but it's really just a lot of basic arithmetic, so hopefully you'll be able to get through it. Let me know if you have any questions, and we'll continue with this lesson next time.